Okay, so welcome to the third video for Chapter 9, the second video for Section 9.3, least squares regression. So please pause, copy this panel down, and then press play. All right, so if you recall from the end of the last video, where we were at was B was the slope of our linear regression model. And we had it written as the correlation coefficient times the sample standard deviation of y over the sample standard deviation of x, okay? All right, well, with this idea in mind, we say that the variables x and y are perfectly correlated if r is equal to 1. Because if r is equal to 1, then this slope becomes 1 times sy over sx. So that's our slope. So that means if I change the x value by 1 standard deviation of x, it forces a y change of 1 standard deviation, okay? So it's not saying if x changes by 1, y changes by 1, but it's saying that if x changes by 1 standard deviation, then the y value will change by 1 standard deviation, okay? All right, so now we're going to get into something, an analysis of what else r is actually telling us, or more actually r squared, okay? So what do we mean by variation? Variation is how the actual data differs from its mean, right? We vary from the mean. So variation is y sub I minus y bar. And if you note, I can algebraically adjust this by subtracting a predicted value of y and then adding the predicted value of y, predicted from our linear model, okay? So I've got to that equation. And now via some fancy algebra, which you can find online, I can take the sum over all my data of the variation squared, we call that the total variation, and show it equals the square of the residuals, the yi minus yi half, that's the residual, the error from the actual y value and what our model is predicting. So that's the variance of the residuals added to the variance of the predicted values. So that's where my predicted values vary from the mean of the data, which, as I mentioned in the earlier video, is also the mean of the predicted values of y, okay? So from here to here, I have some fancy algebra, but it allows me to write the total variation as the sum of the variance of the residuals and the variance of the predicted values, okay? All right, so let's lock in on the variance of the predicted values down here. Now, the yi half, the predicted value of y, that's the linear function, a plus b times xi. And y bar, we knew from the earlier video, is just obtained by putting x bar into that linear regression model. So a plus b x bar, okay? Now note the a's cancel. I can drag a b out, and it takes the square, and then I have the xi minus the x bar squared. That b squared can come out of the sum, and the sum of xi minus x bar squared is what we've been calling SSX. And we learned that that was equal to r squared times SSY in the earlier video, okay? All right, so I've got then, starting with this statement E equaling this statement in R. If I solve for r squared, I'm going to take the SSY and divide it underneath that, which is what I've got written here. And SSY, by definition, is this sum, okay? All right, so I have r squared is equal to this fraction. The numerator is the variance of the predicted y's, right? It's the predicted y value minus the mean of the y values squared. The denominator is the variance of the observed y's. It's the actual y's minus their mean squared, sum over all the data, okay? So r squared is telling us the variance of the predicted y's divided by the variance of the observed y's. In other words, r squared is the proportion of the observed variance explained by the linear regression. Observed variance is the denominator, and the numerator is the variance of the prediction, variance of the model. So r squared times 100% is telling us how much of the variation of the observed y's is explained by this linear regression that we've created, this yi hat equal a plus b times xi. So r squared is measuring how close our model is to explaining the variance of the data, which is kind of cool. Okay, so why don't you pause, copy this panel down, and then press play. There's one bit where I refer to R, but I'll probably not do that until the next panel as well, okay? All right, so as an example of what this R-squared is telling us, if we look at example 9.3 in the textbook, we've got the black spruce data, where we're seeking to model the change in the diameter of the tree trunk as a function of the change in the height of the tree, right? So we have this change in diameter, we have this change in height, change in diameter data set. We set a linear function to it, a least squares regression line of best fit to it, and we have R calculate the R-squared value. So, and I'll show you this when I move to the R code in the next panel, but we got R-squared is equal to 0.8138. So that is telling us that 81.38% of the variability of the diameter change in the actual data set is being explained by this least square regression line of best fit on the height change. So our model is capturing 81% of the variability of the actual data. Okay, that's not bad. That would be nice to have it in the 90s, but not too bad. And just for note, if you look in the R code, here is the command for that. This to give us the linear model. LM is linear model. I want diameter change as a function of height change, and the data is from spruce. And I'll go through that in the next panel. Okay. All right. So we now know how to calculate A and B. In other words, how to calculate this least squares regression line of best fit. We know how to calculate R-squared, which is telling us a little bit about how well the model is fitting the actual data. And here's another way of sort of looking at how well the model is fitting the data. Okay. So another way to check this goodness of fit is via a residual plot. Now, a residual, if you recall, is if I've got a predicted value of the y's from my linear regression model, I can compare it to the truth, and this difference is called the residual, okay? And then, which is another word for error, and then I could plot all of these residuals on a plot, and that's called a residual plot. And if the model is a good fit for the data, I would hope to not see any patterns in this residual plot, and I'd hopefully see as many residuals that are positive above the zero line as are negative below the zero line, and no discernible patterns, sort of just kind of random hovering around the zero line. So I can use a residual plot to test how good models fit, and I'll show you one in a minute. Last panel. All right, well, not much to copy down here. It's mostly going to be me going to R in a minute here, but if we look on page 313, table 9.1, we see some residual plots, and I'm going to show them to you on the screen. Okay, so if you look here in A is a residual plot. The horizontal line is the zero line, and we see it looks pretty random, and it looks like we've got about the same number of points above the zero line as below the zero line. So that residual plot is showing us the linear regression model seems like a good fit. In B here, we see that most of the residuals are negative. Most of the residual plot points are below the zero line. So that's probably not a good linear regression model. In C, we see a nice scattering above and below, but we see one outlier that's way out of line with the others. That indicates, well, maybe a slight problem with the model, or maybe we should just kick that point out and recalculate our linear regression model. And finally, in D, this is sort of showing a pattern in the residuals. If you note, it looks like we've got this sort of parabolic or V shape going in the residuals. That might indicate, if it's parabolic, that a line is not a good model for this. Maybe a parabola is a better model for this, right? So maybe a linear model of best fit is not appropriate. All right, so now I'm going to go and show you a couple of R commands for this data that's in the chapter 9 folder. So screen share, RStudio. All right, so line 24 here, that's the start of the example when we put through the spruce line. So this command is going to designate spruce.lm as a linear regression model of spruce. And again, it's modeling the diameters change as a function of the heights change. So I'll run that, and I'm going to run this spruce.lm command to show you the output, right? Okay, and if you know, down in the bottom left, it says the intercept is minus 0.5189. So that would be my A value of my model. And the height dot change, that's the b that sits next to the height dot change variable. So that's the slope of my linear model. It is 1, 4, 5, 9. Okay, so I can also then plot the residuals, which would be line 33 here. And there you see it, and the very next line 34 puts in the 0 line. All right, so if we look at the residuals model, it looks pretty good. It looks like we got an equal number above and below. If I'm going to quibble, which I could say that, well, it looks like on the extreme left and the extreme right, the residuals tend to be positive. And in the middle, the residuals tend to be negative. So that maybe there's sort of this parabolic shape that would fit the data better, all right? Okay. And then if I go to example 96 from the book, I've got 20 grains of vanilla ice cream in this model, and I'm going to measure the sugar content of, I don't know, a spoonful of each and the fat content of a spoonful of each, and I'm going to link sugar and fat together. And what I'd like to do is I'd like to create a linear model that predicts the fat content as a function of the sugar content, okay? So I've got my sugar vector. I'm going to let R know what that is. I'm going to link it to this fat vector. We can do the means. So there's 17.6 grams on average of sugar. There's 11.6 grams on average of fat. I can do standard deviations. And I can do my correlation coefficient of 0.79. Now remember, if I square that, that's going to tell me what percentage of the variance is explained by a linear regression model. So let's actually calculate a linear regression model. So here my command is lm fat vector as a function of sugar vector, okay? All right, so my intercept, the A value of my model is minus 3.7142. And the B value, my slope, B sits next to the sugar variable, so that B value is 0.8669. Okay. All right. So this is how we will be using R to figure out our linear regression models. Stop share, stop video.